audible? So yesterday we saw stable matching and we proved some results related to stable matching. Sure, stable matchings are very desirable in the sense that no two vertices have any reason or incentive to break their current matches and pair up with each other. So stability is a desired property, but it has its own drawbacks. So for example, stable matching can be small. I mean, we have seen that they may not be maximum, of course, but they can be quite small. So just to see how small, let's again recall what we saw yesterday. So I will write bigger. And here if B1 has a first preference for A2 and A2 has a first preference for B1, then this gives us only a one size matching. So this matching is stable, but it has size 1, whereas the maximum matching has size 2. And in fact we can have many such components so that the stable matching will be just half the size of the maximum matching. There are lots of applications where this is not a very desirable or very much acceptable situation. For example, while allotting elective courses to students, or while allotting doctors to hospitals, one would prefer that lots of them are matched so that the hospitals also get doctors and doctors also get positions. So our question today is there a way to compromise a little bit on stability and gain in terms of size? So let me write down that stable matching can be as small as half the size of a maximum matching. So the question we want to address is, can we compromise a bit on stability in the interest of size? So a bit is still undefined. I will put it in quotes. So of course we need another notion of optimality. We don't want to also go to the other extreme and say that we will just find a maximum matching and don't care for preferences of the vertices. So we don't want to go to that extreme. So we will define another notion which is a bit relaxed, as we will see. So the notion that we will define today is popularity. So this is so stability is a very local concept. Right? For every pair of vertices, we say that they should not prefer each other over their current partners. Here we don't become that strict. We look for an overall stability in some sense, or overall optimality. So what is popularity? Here we take votes from vertices and ask them which matching they prefer between two. Okay, so it is like taking majority vote. So if majority of people are happy with our current matching, we will just go with it. So although it may leave some unhappy pairs or unstable pairs, it will still make majority of people happy. So let me formally define it now. So let's say PQ are two matchings. And the vertices are asked to vote between P and Q. Of course, they vote based on their preferences. If they get a more preferred match in P, they will prefer P, and otherwise, if they get a more preferred match in Q, they will prefer Q. and whichever matching gets more votes, we will say that that matching is more popular than the other matching. If P gets more votes than Q, then we say that P is more popular than Q. So right now, yeah.
Sorry, could you please explain why stable matchings are at least half?
At least part I did not prove. So actually stable matching are maximal matchings because no endpoints of a single edge are left unmatched in a stable matching. So that gives at least half part. Yeah, so we did not prove it. Maybe we can try to prove it in the tutorial session. That any maximal matching you take, it will be at least half the size of a maximum matching. Intuition is that if say a maximum matching has k edges and matches 2k vertices, then both the endpoints of an edge cannot be unmatched in any maximal matching because then that edge can be added. So if a maximum matching matches 2k vertices, at least one endpoint of that edge should be matched in any maximal matching. So that gives us that at least k vertices should be matched in any maximal matching. The size should be at least k over.
So, like a quick follow-up. So that also implies that if you take any maximum matching, the set of vertices that it matches is a superset of the set of vertices a stable matching matches. Right.
That may not be the case, right? For example, if we have an instance like this, so I will just draw the graph and not the preferences. But yeah, so stable matching may also turn out to be a maximum matching, but sure, as in if this is stable, there is also another matching which has same size but it may not be stable. Both are maximum, but what I am saying is still every maximum matching may not be stable.
No, so I'm just saying that the set of vertices any maximum matching contains is a superset of vertices that any stable matching contains. I'm not talking about the edges here.
Yeah, I'm not sure about the any part. Maybe for any stable matching, there is of course a maximum matching which matches the whole set of vertices and some more. Yeah.
This motion is not necessarily for stable matching.
The basic setup is same, that there is a bipartite graph and vertices have preference list over their neighbors. So again, the same setup is there. The same graph, you can also find a stable matching, but now we are looking at another notion which will possibly give us a larger size. And actually, the way I have defined it looks like this is completely unrelated to stable matchings, but it is not. And as we go on, we will see that. Okay, so here we don't ask pairs of vertices whether they prefer each other over their partners, but overall we take votes between vertices, votes from vertices between the two matchings. Whichever matching gets more votes is more popular, and then we define a popular matching in the instance. Is this color visible? Okay, I will take another. We say that a matching M is popular in a given instance. So when will we say that a matching is popular in the whole graph? We would like it to get more votes than every other matching. So that is a bit too strict, but we will say that at least there is no matching which gets more votes than this. So equal votes we allow, but no matching should get more votes than it. If no matching n gets more votes than.
Sorry, will you use another pen?
Sure.
Thank you.
Maybe green color is not a good choice, is it? I'll use red one. This is good, right? Sure. Okay, so we have defined popularity here. Let's look at our example, this example, where the stable matching is just A to B1. So let me write down the preferences if they are not clear. So A1 and B2 anyway have only one neighbor, and let's say B1 prefers A2 over A1 and A2 prefers B1 over B2. So this matching, just single edge matching, is a stable matching. The only other matching which is present is this matching, right? A1 B1 and A2 B2, which is obviously unstable because A2 B1 is a blocking pair. But let's ask, is this a popular matching? So let's take the votes just for an to see whether we are gaining anything when we talk about popularity. So the two possible matchings are these. One matching is A2 B1 and another matching is A1 B1 A2 B2. Let's ask vertices to vote between the two. So all these vertices will cast votes. Can you count the votes quickly?
How do we go from the ranks to the votes?
Yes, so in this matching A2 gets first choice, whereas in this matching A2 gets second choice. So A2 will prefer M over N. Okay, so a better rank means vote towards that matching. So again A2 gets first choice here, whereas second choice here. So A2 is going to vote for our first matching, that is M.
So one more question.
Yeah.
So in the definition of a popular matching, is popular in a given instance if no matching n gets more votes than n in a one-to-one contest.
Yes.
Right.
So it is always one-to-one comparison. So one might think that we have to go over all pairs of matchings and compare and then figure out. No, we have algorithms to actually find out a popular matching. So we will see the algorithm in a short while once we are fine with the definition. So yes, popularity actually involves pairwise comparison. So it is not immediately clear how to check whether a given matching is popular or not. But nevertheless, we will see an algorithm and we will prove that the algorithm outputs a popular matching. Okay, so coming back to our vote count, A2 is going to prefer the first matching, that is M. It may not be transitive. Yeah. Well, we'll see. I mean, we'll not see right now, but on the face of it, it's not clear why it should be transitive. I mean, I don't have one example at hand right now, but it doesn't necessarily imply transitivity. So B1 is also going to vote for the first matching because again B1 gets first choice here, which is A2, and B1 gets second choice here, which is A1. So who is going to vote for the other matching? A1 and B2 are unmatched here. So here they are at least getting something. They are going to vote for it. So in fact, in this small instance, we see that both matchings are popular. No matching is I mean, M is popular because N doesn't get more votes than it, and similarly for N. So our stable matching also turns out to be popular, and also there is a larger matching which is popular although it is unstable. So this tells us that popularity might give us larger size matchings. Any questions so far? Anything about the definition? Okay, now let's ask the next question. How does the set of popular matchings compare with the set of stable matchings? So here of course the set of popular matchings is larger. It also contains the stable matching. Whether that is in general true, or can it happen that some stable matching is not popular? What do you think should be the case? Is it too small to read?
Just the preferences for the matching on the lab.
These are the preferences.
There are. Okay, sorry.
Yes. I think you can move forward because you are too much at the back. And today fortunately we have space. Okay, so this is the question: can a stable matching be not popular? So if a stable matching is not popular, there must be another matching which is more popular, which gets more votes. So let's say P is our stable matching that possibly is not popular. And let's say Q is a matching which is more popular than P. Now, if a vertex gets the same match between, same partner in P as well as Q, that vertex is not going to vote. It will just say, okay, I am indifferent, you can go ahead with other votes. So the only vertices that will vote are those which get different partners in P and Q. So let's look at our stable matching P. So let's say these are the edges of the stable matching. Now this vertex might have a different match in Q. So these are plane edges are Q edges. This vertex will of course possibly have a different match in Q, or it may not even have a match. So for example, something of this sort. Okay. And now let's see if Q is more popular, what all are the vertices that can possibly vote for Q? Exactly. So these vertices will definitely vote for Q. This one and this one, because they don't get any match in any partner in P, whereas they are getting at least some partner in Q. So let's look at any edge of Q. So consider this particular edge. Can both these vertices, so let me call them say A2 and B1. So can A2 and B1 both vote for Q? Exactly. So P is a stable matching and this edge will otherwise be blocking P. So A2 and B1 both cannot vote for Q. Even for this edge, although this endpoint votes for Q, for the same reason A1 cannot vote for Q, right? A1 has to vote for P, otherwise A1 and let me call this B0. Yeah. A1 B0 will be a blocking pair. So for every edge of Q we can say the same thing, that is if one endpoint votes for Q, the other one must vote for P. So for any AB belonging to Q, only one of A and B can vote for Q, other has to vote for P. And this follows from the stability of P, because otherwise if both vote for Q, they will make P unstable. But then how does Q get more votes? For every edge where Q gets 1 vote, it also loses 1 vote. So as it turns out that, because of this, that along any edge, Q gets 1 vote, at most 1 vote, and loses 1 vote. It may also happen that A2 and B1 both prefer their match partners and nobody prefers Q. That is perfectly possible. But at least one of them has to vote for P. So Q can get at most 0 votes along any edge. It can get at most 1 vote, but it has to lose the other vote. So Q cannot get more votes than P. So if you observe, Q cannot get more votes than P. And which means for any stable matching, there is no other matching which gets more votes than that stable matching. In other words, by our definition of popularity, stable matchings are popular. Any question, confusion? You can feel free to ask and we can clear it. Is there any confusion? Sure. Is everyone convinced that stable matching cannot lose when it comes to voting against any other matching? Okay, so this is a nice thing in the sense that earlier we accepted stable matchings and now at least that set we are not losing. And as we saw in this example, it's not that set of popular matchings is exactly same as stable matchings. There are larger matchings also which are more popular. So the set of popular matchings is possibly strictly larger than set of stable matchings. So these are all stable matchings and these are the popular ones. Right, so for example, this matching A1, B1, A2, B2, this is not stable, right, because A2, B1 is a blocking pair. But then it doesn't lose against the stable matching. It is also popular because there is no other matching which is more popular than this. Okay, so now how do we find a popular matching? Of course, we cannot keep taking matchings and comparing and asking for votes. On the other hand, the example that I had just drawn, maybe I will redraw it. So A1, B1, A2, B2. So A1 prefers B1, A2 prefers B1 and B1 also prefers A2. I hope there is no ambiguity about the ranks that I have shown here. Because anyway A1 and B2 don't have ranks. Okay, so here even this larger matching is popular. The question is what makes that matching popular although it is unstable? Yes, but indeed although it is unstable it is still popular, right? And if we want a larger popular matching, we have to settle for instability because yesterday we saw that all stable matchings have the same size. And in fact they match the same set of vertices. So now our goal is to get a larger popular matching and of course settle for some instability. So this example suggests that for this larger matching which is unstable, what makes it still popular is essentially the votes of these unmatched vertices. The vertices which form the blocking pair vote against that red matching, but indeed the unmatched vertices vote in favor of it, and that is what makes it popular. So that is the basis of the algorithm that we will see. So we will of course execute Gale-Shapley algorithm and find one stable matching, but then we want to exploit the fact that if there is a larger matching which matches more vertices, we can possibly get, we can still be popular, and that will be a larger matching. So what we will do is, we will execute Gale-Shapley algorithm. So now this is the algorithm to find a maximum size popular matching. Clearly not all popular matchings are of the same size, right? Because even this stable matching A2B1 is popular. Similarly, this larger matching A1B1 A2B2 is popular. Maximum size popular matching. So first of all, we will execute the Gale-Shapley algorithm, and now whichever are the vertices like this A1 that are unmatched in that after finishing this Gale-Shapley algorithm, what we will do is we will give them a higher priority and ask them to propose again. So unmatched vertices, say A in A, get higher priority. I will tell what higher priority means. And propose again in the order of their preferences. So how does it make a difference if they propose again? Of course, all the B's have their more preferred matches because they have been rejected already. But now we will say that once a higher priority vertex proposes a vertex B, that vertex has to prefer it over any other low priority vertex. So the next part I will write here. So any B in B it is kind of compulsory for them to accept a higher priority vertex over a lower priority one. Or a normal priority one. So let's try this on this small example. Okay, so here I will execute the Gale-Shapley algorithm first. So this is just the example where B1 prefers A2 over A1, and again A2 prefers B1 over B2. So A1 will propose to B1. For now B1 will accept because there is no other match for B1. B1 has no other proposal. But when A2 proposes to B1, B1 will compare and reject A1, okay, because B1 prefers A2. Now A1 remains unmatched and A2 never proposes to B2. Now our second stage will start. So this was the first stage. Now let's go to the second stage. A1 is unmatched. We will give a higher priority to A1. We will denote the higher priority by star. So A1 has become a star now, or it has achieved a star status. Now when it proposes to B1, this rule says that B1 has to accept A1 star over A2 because A2 is still with normal priority. So now B1 has to reject A2 and accept A1 star. What will A2 do?
A2 has to separate from.
Say it again.
It will not ask the same rejected class.
A2 who will not ask A1 star?
I think A2 is rejected, right?
Yes, and there is no point in asking again, right? Because B1 has to prefer A1 star over A2.
So A2 will ask B2.
Yes, so A2 has not yet finished preference list, otherwise A2 would also have had a star status. But A2 has still B2 left to propose. A2 will propose to B2 and B2 will accept.
What if there are like several stars? So so among the stars also they maintain the same priority order?
As the preferences.
Okay. It's a higher level but still the same order.
Yes, so within normal priority, it's the same preference order that the vertex has. Within higher priority also, it's the same preference order which the vertex has. Yeah, one second. Yeah.
So when do we know when to stop the algorithm?
Yes, so good point. If at all A1 star had been rejected, maybe because some other star vertex also proposed B1, I can draw that example. Maybe. So suppose there is also A3 and B1 gives second choice to A3 and third choice to A1. So let me write down this preference list. So B1 gives A2 the first choice, A3 the second choice, A1 the third choice. Okay, so consider this modified example. Now what will happen? A1 star will propose to B1, sure B1 will accept now. A2 will go to B2, but then A3 also is unmatched and A3 star will also propose to B1. Now what will B1 do? B1 will check between A1 star and A3 star. It prefers A3 over A1. So it will reject A1 star and accept A3 star. So our matching will in fact not be this matching, but this matching. So here A1 has also remained unmatched even after getting star status. It has to remain unmatched. So instead of every vertex proposing once, here every vertex is proposing at most twice, and then the algorithm will stop. You had a question.
Yeah. In the original graph, A1, B1, A2, B2, if B2 wasn't there and you run this algorithm, it's going to match A2 to B1. No, sorry, A1 to B1.
Yes.
That is not more popular than matching A2 to B1.
So the matching that we are getting here is not going to be more popular because stable matchings are always popular and no matching is more popular than a stable
No, but it will
matching.
be less popular, right?
It will not even be less popular, right? Because A1 will vote for this matching.
Yes, B1
Oh, sorry.
and A2 will vote.
No, wait. I think let's draw this. So A1, B1 and only A2 but no B2.
Yeah.
Now what will happen? So B1 prefers A2. So A2 B1 will be the first round of the Gale-Shapley algorithm. Even if A1 proposes, A1 will get rejected. Now A1 star will propose to B1. This will get accepted and it has to reject A2 because of this rule of ours. Now A2 has exhausted the preference list, but A2 didn't become star yet, right? So it also can become star.
Oh, it can also become star.
Yes, so any vertex has the right to finish these two rounds, one without the star status and one with the star status.
We won't allow a double star maybe if they get.
No. So actually that is a nice question and in fact that might give us a matching which is not popular. So if we up to single star we retain popularity, but if we do another round with a double star, that can give us matchings which are not popular. That's a good exercise to just think and come up with such a small example. Okay, so every vertex has the right to get a star status if it is rejected by all the neighbors with a normal priority. That way we will avoid these less popular matches. Any other question? Any confusion about the algorithm? So asymptotically it is just two rounds of Gale and Shapley. So the time complexity will be similar to that of Gale and Shapley. Just one more extra round, but that will not add to the time complexity. Alright, so the next task is now to show that whatever we are getting is indeed popular and it is not going to lose votes against some other matching.
Also,
Yeah.
you have to perhaps again check that the order doesn't matter in which when we execute this algorithm in the start phase.
That is true, but that I think will be more or less a similar argument as the Gale-Shapley algorithm. So we will not prove that argument really, but it will be the same argument like this. Because even with star status, independent of when a vertex proposes, it is going to, I mean, among star vertices also it is same Gale-Shapley algorithm that is being executed.
Right.
Maybe I will just execute this once more on a slightly bigger example. Not so trivial one, but somewhat more interesting. And there are these edges also. And then there is an edge here, there is an edge here. And now let me write down the preferences. A1 prefers B1 over B2 over B3. A2 prefers. Maybe this is a good thing that you can try the same algorithm on this. A2 prefers B2 over B1. A3 and B3 have no preferences. B1 prefers, let's say, A2 over A1. B2 prefers A1 over A1 over A2 over A3. Can you see what output we might get? Yeah.
After the initial Gale-Shapley, if someone with a higher priority proposes, then whatever their rank may be, it will accept the.
Over normal vertices, it has to accept a higher priority vertex. So,
Whatever the rank may be.
whatever the preferences are, yes. But within vertices of same priority, either two vertices with normal priority or two vertices with higher priority, the preference ordering will be applied. So, can you tell what you get here? I think now everybody remembers the definition. I will erase this part and everyone found the output?
The start process of the one was remain unmatched in the stable matching.
Yes. But even other vertices who might exhaust their preference list because they are displaced by the star vertices, they can also get star status later. So let's try executing on this. What is the first stable matching that you get? A1, B1, A2, B2, right?
No, I think it's A1, B1 and A2, B2.
Yeah.
But are a stable matching.
So first Gale-Shapley round gives us A1, B1, A2, B2. Is everybody fine with this, or does anybody get anything else? Yeah, because A3 will propose to B2, but B2 will reject A3 over A2. And B2 prefers A1, but B2 is not getting a proposal from A1 because A1 has proposed to B1 and B1 accepts.
So we are starting from A1.
We are executing an A proposing algorithm. So A1 proposes to B1, A2 proposes to B2. They get accepted, and now A3 just gets rejected. So there is no way for B1 to get A2 or for B2 to get A1. So you can see that is another stable matching.
Matching which is the other way, the diagonal.
Yes, if we had B proposing, we would have had.
We would have had one.
Yes. So yeah, this is the Gale-Shapley round. A3 remains unmatched. So now A3 star will propose. A3 star will propose to B2. Now B2 is required to accept. So B2 has to reject A2.
But now A2 will become A2 star.
No, A2 has not finished preference list yet. Right?
No.
So A2 should first propose to B1. Okay, A2 will not get a star status at this point because A2 still has unproposed vertices in this preference list. A2 has never proposed to B1. So A2 will first propose to B1.
B1 is happy with that.
Yes, B1 is happy to accept A2. So B1 will reject A1 and accept A2. What will A1 do?
Now A has to propose to B3.
But A1 has not proposed to B2, right?
No, it has to propose to B2 also.
B2 and B2 will accept.
Will B2 accept?
Yeah, it is higher priority.
A1 doesn't have higher priority yet, right? See, A1 got rejected from here, but A1 doesn't get higher priority at this point because it is yet to propose leftover vertices. I mean, there are leftover vertices in A1's preference list. So unless the preference list is finished, no vertex gets a higher priority. Okay, so A1 has to now propose to B2. But what is B2 going to do?
B2 is already from the higher priority.
Yes, so B2 is compelled to accept a higher priority vertex or prefer a higher priority vertex over a normal one. So B2 cannot accept, although B2 likes A1 more than A3. Now A1 still cannot get star status because it is yet to propose B3 with normal priority. Okay, so A1 proposes to B3, but B3 accepts. So A1 doesn't remain unmatched with normal priority. A1 is not going to get higher priority or star status. So this is the final matching. Now everybody is matched. So A3 star is matched to B2, A2 is matched to B1, A1 is matched to B3. Yeah.
One of the examples, if A1 does end up getting a star status, we then continue the algorithm.
For example, if this B3 was not there, then A1 would have had a star status.
And we have to continue.
Yes. So there are two rules. I will write them down. So every vertex must finish the whole preference list or must propose everybody on its preference list before getting a star status. Unless the preference list is finished and that vertex is rejected by everybody, it will not get a star status. Status meaning the higher priority. And secondly, every vertex that remains unmatched even with star status just remains unmatched. Any more questions or confusion? Yeah. Yes, so for Gale-Shapley algorithm, we saw that the proposal order doesn't matter. Similarly, even with star status, it is just Gale-Shapley algorithm. So the star vertices among themselves are executing a Gale-Shapley algorithm. So by the same argument for the algorithm that we saw yesterday, the order of proposals will not matter here as well. Yes. Yes. So I think the proof will go similar to the way we did it yesterday. Yeah, so there are various things to prove. First of all, that the matching output after this whole exercise is indeed a popular one. And secondly, actually it is a maximum size popular matching that this algorithm outputs. So any larger matching is actually not popular. So we will probably show only the first part, that is the algorithm outputs a popular matching. And interestingly, as someone pointed out, if at all we give yet another double star status, that doesn't give a popular matching. So I think that maybe at some point you should try to create an example. Okay, so I think this is a good point to stop, and we will see the proof of popularity in the next session, and Meghna will continue with that. Yeah.
If we go for another star, for double star, does it come back to the stable matching?
It can get a larger matching. In fact, what you can prove is that the more star status you give, the matching can become larger, but it will not be popular. So since we have a few minutes maybe up to coffee break, I don't see Atas here. I will mention a few things as closing remarks from my side. So first of all, what we have covered here is only like scratching the surface. So there is lot of literature that on stable as well as popular matches. I will mention a little bit here. So there is a book which is called Stable Matching Structure and Algorithms, which has many more results on stable matching. So those who are interested can explore this further. Also, for popular matches, actually there are lots of papers showing various things about popular matches. One which I would say a good starting point is this is a paper, a size popularity trade-off. In the stable marriage set. Stable matches are also called stable marriages in literature. And this is a paper by Kavita. If you search for popular matches, there are a lot more papers and lot of things people do with it. This is a basic one. So, yeah, we'll stop.
You can continue if you have anything, you know, time, but you can tell me also.
How do you stop the record?
Like you have something that works. So instead of the quant finance and quant gambling.
Okay, we'll start the second session. Okay, good morning, and so we'll continue where Prajakta was left. Our goal in this talk is to show properties about the output of the algorithm. So I believe that the algorithm is very clear to everybody. You have also executed it on multiple instances. But if there is a doubt, you can raise it later. But now we will say that we are given this instance G, which is the same as the stable matching instance, but we have run the Gale and Shapley algorithm and then given this higher priority and run the modified Gale and Shapley algorithm and obtained the output M. So M is the output of the modified Gale and Shapley algorithm. Is this writing okay? This is okay. Okay, so what is our goal? I mean, what do we have to do here? We know how to run the algorithm. So show that it is popular. In fact, it can be proved. We may not do it. We may not do both the things. So yeah, I think in the first class project I had drawn this set of stable matchings. This is inside. This can be strictly inside. The set of stable matchings are here. The set of popular matchings, this is the set of popular matchings. And we have seen that popular matchings can be of different sizes. We have seen an example where there was a popular matching which was also stable of size 1. And there was a popular matching of size 2 which was not stable. So in general, this set, which is this larger circle, can have matchings which have different sizes. So ideally it would be nice to find a matching M star here, which is of course popular, but which also has largest size in this entire set. So that is what we would like to find. So the stable matchings may be of smaller size as we have seen in the example. There can be popular matchings which are not stable of different sizes. And ideally we would like to find a matching which has the largest size and which is popular and has the largest size among popular matchings. Indeed, the algorithm does produce such a matching, that is in this bigger circle or in this set of popular matchings, it is the one which has the largest size. But first we will just try to prove that it is popular. Right? Okay. So our goal is to prove that M is popular. Any thoughts on how does one prove such a thing? Yes.
Should have the same number of votes as the stable matching in the first round of equation. If M is popular, then it will have the same number of votes.
Okay. So recall what is the answer is that it must have the same number of votes as compared to the stable matching. So, but what is the definition of for a matching to be a popular matching?
It is a matching which is more votes than this one.
Yes. So just having the same number of votes doesn't satisfy that, right? So it may have the same number of votes, but there may be another matching that beats it with respect to other votes. So we already, and Rajat also mentioned that it need not be transitive. The relationship need not be transitive of the votes, and the more popular than relation need not be transitive. So therefore, what we want to show is that there is no matching N that beats M in votes. Is this okay? Yeah, you had something.
I don't know if it's correct, but like, should we show that all the intermediates are popular?
What is intermediate?
Like after the first iteration of the Gale-Shifley algorithm, all the intermediates that we get, they remain popular.
Okay, it's a good suggestion. Yeah, okay, so we start with a stable matching which is popular and we never move out of that set. But is that true?
I don't think it's true.
I mean, intermediate we go to some matchings which need not be popular. So that is something that one can verify. So the suggestion is this, that the Gale and Shapley gives a solution. You are at a stable matching which happens to be popular, and then when you are doing this higher priority business, do you remain always in that set? That is something for you to verify. Okay, any other suggestion? Okay. Okay, so note that I mean this is we have one candidate matching at hand, and we want to show that no other matching N beats M. So it doesn't suffice to show one matching that doesn't beat, or with one matching we have equal number of votes and so on. In fact, to show that some matching is not popular, it is fairly easy, because you can show another matching that beats it in terms of votes. But to show that some matching is popular, you need to do more work. Yes.
Maybe try something like a proof by contradiction. Assume that there is a matching which has some highest number of votes and show that this M is either reaching that number of votes or it exceeds that.
Yes, yeah, sure. We are going to try something like that. Good. So we are going to kind of say that, okay, if there is a matching that beats M in terms of vote, how does it look like and why does it beat, and then appeal to the steps that we used in the algorithm.
So
Right?
is M unique, or there could be a N which equals M as well?
There can actually, so equals meaning in terms of votes, right? So that we have already seen, right? A stable matching which was of smaller size. So I'll keep this running example here, which is what I think Prajakta drew, which is A1, A2, B1. So this edge was not. Yeah, possibly this edge was present, and B2. And these two were 1, 1. This is 1, 2, and this is 2, 1, right? So the stable matching is A1, B1, which is, I'll call it MS, which is, sorry, A2, B1, which is the stable matching. And after running this modified Gale and Shapley algorithm, you get M, which is A1, B1, A2, B2. Is that right? So the votes the votes are the same, right? But that doesn't mean that for all instances, and on this small instance we have verified that M produced by our algorithm is indeed popular. But how do we know this for a general instance? Okay, yeah, that is what we want to show. Okay, so yeah, so we would like to look at the structure of the or we would like to investigate more on how our matching is with respect to what has happened during our algorithm. So remember that A is the set of vertices on the A side, B is the set of vertices on the B side, and during the course of the algorithm, some vertices in A got this higher priority, and they were called as A star. Not every vertex necessarily got a higher priority. So whichever vertex got higher priority, let's put it in a different set which we will call as A1. Right? So A1 are the vertices which at some point got higher priority, and they only can get a star, they don't get double star. Once they get a star, they always remain at that star status and they don't come down. Right? Similarly, if a vertex, let's call it A1, some A2 did not get a star, we will put it in A0. So there are these two sets. That is, so all the vertices that got a star a higher priority are here, and all remaining vertices in A
this can equivalently be written as A naught is equal to A minus A1. Right. Yes.
So given A and implementing the Giuseppe algorithm for the A optimal way, is A1 unique? Because if you choose a different order to the with the start vertices be the same set.
Yeah, so we can argue that it doesn't change. But let's say that you ran your algorithm in a particular way. Whatever vertices got star status or higher priority, call them A1. For another, let's say, since we did not prove, if somebody else ran it and they got a different set for the sake of this assumption, let that be their set A1. So your set A1 and A1 and for some other friend of yours.
With respect to my implementation.
Yes, your execution.
Sorry.
Your execution of the algorithm, right? So all the vertices that got a higher priority in your run are called A1. The remaining vertices in A that did not get higher priority are called A0, right? So this kind of partitions our set A as A1 and A0. And it seems also natural to partition B vertices, but the way we will partition B vertices is the following. So let's ask the vertices which are put into this set A1 and ask them, are you a matched vertex in the final matching that the algorithm produced, the matching M that was produced? And if so, what is your matched partner? Put that matched partner in the set B1. Right? I'll just make this slightly closer. Okay, so is the set B1 clear? So you look at all the vertices that were put into the set A1 and ask, are you a matched vertex in the matching that was output? If it is a matched vertex, what is your match partner? Put it into the set B1. Okay, so there seems to be some question. Okay, sure. And again, so B1 are the vertices which are matched partners of vertices in A1, and B0 is again the remaining B vertices. So I'll just write it as B minus B1. So we have these four sets A1, A0, B1, B0, and let's start with this set A1 itself and ask, can there be a vertex which is not matched in the set A1? Can it be left unmatched after our execution of the algorithm? Yes, right? So there can be unmatched. So I can draw this representative vertex which is not having any matched partner. So there can be unmatched vertices here. So A1, this can contain unmatched vertices. Right? What about this set B1? Can it contain unmatched vertices? Yes, no? No. Right? Why cannot it not contain? Because the way we have defined it, they are matched partners of vertices in A1. So if you have been put into this set, it must be because you are matched to somebody in A1. So therefore you cannot have. So this set cannot have does not have unmatched vertices. Now let's ask vertices here. Can vertices in A0 be matched? So all of them have to be matched? Why?
Rejected and got star.
If they were not matched after completing the execution of the algorithm, then they should have been starred and they should have raised their level. Maybe they still remain unmatched, but then they go to the set A1. So therefore every vertex here is a matched vertex. So it has a matched edge. So I cannot draw such vertices here. What about B0? Can it have unmatched vertices? Again, it can have unmatched vertices because we just put everything that was remaining in B as B1. So this thing that is A can contain unmatched vertices is true about B0. So I will not repeat this. So this is true here also, and this thing is true about here. That does not have unmatched vertices. Right? So these vertices are always matched. These vertices are also always matched. There can be unmatched vertices here. So this is how the set of vertices arrange themselves with respect to this partition. I have done nothing new. We took the algorithm, executed it, and just thought about the set of vertices arranged in this way. And it also looks clean. Because of this arrangement, all the matched edges always remain horizontal. That is, they are going from A1 to B1 or A0 to B0, but not crossing across these sets. Anyway, edges are between the two partitions, but yeah. And there are unmatched edges also, right, in the graph, which are not being matched. So where are they? They can be inside this set, they can be here, they can be across these things, and they can be here. They can go here. Right? So our goal is to kind of analyze the status of these edges, and I'll also say why these edges need to be analyzed. Right? Okay, so it is here. Is there any question? Okay. So let us say that I have a matching M, which is, let's say I just draw it 3 edges, A1, A2, A3, and B1, B2, B3. I have these 3 edges. Suppose there is another matching that matches these vertices in a different way. Note that it need not match all these vertices. It could leave some vertices unmatched and so on. So how does that matching look like? Maybe it uses this edge A3, B3 as it is. It matches A3 to B3. But maybe it decides to match A2 differently. Maybe it matches A2 to B1. It matches A1 to another vertex, let's say B0, and it leaves B2 unmatched. This could be the case, right? So the blue edges and this edge is also is a different way of matching, and this is another matching, right? So now remember our goal that we want to show that there is no matching N that beats M in terms of votes. So we need to consider all possible matchings which can be obtained by doing various possibilities. So maybe let's just ask, if I decide to use an unmatched edge here in this picture, let's name these vertices. So this is A1, this is currently matched to B1, and this is, let's say, B2. So let's say that I decide to break this match. B2 could have potentially been an unmatched vertex here because it's possible to have unmatched vertices in this set. So suppose I decide to break this A1, B1 edge and match A1 to B2. Right? That's the only change that I do. I have M. I decide to move from M to N by just matching A1 to B2 instead of matching A1 to B1. Right? How does the vote compare between the matching M and the matching N? So between M, which is given by the algorithm, and N, how do the votes compare? So apart from these vertices A1, B1, A2, all other vertices don't care about votes, or they vote the same way. They get the same partner in both M and N, so they are not going to change their vote. So in fact, I don't even need to worry about them when I draw this big voting table. What happens with respect to A1? A1 is going to decide its vote between M and N based on B1 and B2. The preference of A1 between B1 and B2. So let us, for the sake of assumption, say that A1 has its order as B1 followed by B2. There can be multiple things here. So then how will the vote be? Because in the blue matching, or this will get matched and this will remain unmatched. So how will A1 vote? For which matching will it vote? So A1 is going to vote for M because it gets a better partner. What about B2? B2 gets a matched partner in the matching N, which we will construct, but it does not have a black wiggly edge. So where does it vote for? N, right? And what about B1's vote? B1 was matched and it becomes unmatched, so it will vote for this, right? So if I had to look at how do the votes compare between M and N, it suffices to look at this very local part, right? And say that actually M gains better than N, so N is not going to beat. I'm just doing an example, but I hope it is clear, right? Okay, so this can be conveniently encoded by saying that let's look at this vertex which is currently matched in the current matching, which is the black matching. Let us look at any unmatched edge. Let's say this A1, B2. We give a label to that edge, and that label can come from, so the label of the edge of an unmatched edge AB is going to be either plus from this side or minus from this side, and similarly plus from this side or minus from this side, and this is just coming from the preference of that vertex. So let's look at this vertex and ask it whether it is preferring B1 over B2 or B2 over B1. If it prefers B1 over B2, that is, it likes to be matched to its current partner in M, then it resists the change, that is, it doesn't want to change, therefore it will give a minus. Right? If it likes the change, that is, it prefers the change, then it will give a plus. Is it okay? So maybe I'll write this explicitly. So for an unmatched edge, AB in unmatched in M, right? Edge AB. Okay. So the vote of A for B is decided by comparing B with its matched partner in A, which we will write as M of A. So this is a new notation that I am saying. For a vertex which is, for any vertex, let's call its matched partner in M, the matching M, as M of A. If a vertex is unmatched, then M of A is kind of a dummy vertex to which it is matched, and any vertex prefers any true edge or true neighbor over its dummy partner, so that it will always give a vote. So it will give a plus to this edge. It will give a plus, its vote as plus, if it prefers to move along this edge. It will give a minus if it resists to move along the edge, that is, it wants to stay with its M partner. The same thing B will do. The vertex B will also do the same thing. In this example, this could have been plus minus. This could have, what will be the vote of this vertex B2? Given that B2 is unmatched, it will always give a plus, right? So unmatched vertices will always give a plus along any edge. For a matched edge, you will have to look at the preference between B1 and B2 and decide whether this vote is going to be plus or minus. Is it clear? Okay. So when we want to compare any other matching with respect to this current matching M, it kind of, a lot of work is done by just looking at the unmatched edges of that, the edges in that matching which M did not match, and just counting the sum of the votes on its edges. There is a little bit which is not counted. What is that? So we want to build this table, right? The M versus N table. So if I want to build this M versus N table for any matching N, given this matching M, I pick up edges of N which are not present in M, because all the edges which are common, the endpoints vote exactly the same, so they can be discarded. All the edges of N which were not present in M, I pick them up and I look at their vote, I look at the two endpoints, the plus minus labels, and I just add them as +1 -1 and sum them up, and then I'll get the vote that M gets over, how do M and N compare, that table I'll get, but there's something which I have not counted, the votes of some vertices.
Newly unmatched.
If some vertices get unmatched, then their votes don't get counted, and those vertices vote in the favor of the matching M, because they remain unmatched, right? If a vertex gets newly matched, its vote is counted because of the edge, but if a vertex becomes unmatched, its vote is not counted, and its vote has to be it will give a negative vote, because it is going to say that I prefer the matching M over going to another matching where I remain. Is this clear? Okay, so yeah, any questions about how we are labeling? Okay, so then given an edge, it can have all of these 4 labels. There are 2 from A side, 2 from B side, so it can get either plus plus, it can get a plus minus, minus plus, and a minus minus. These are the 4 labels, just exhaustively. So given this picture, we would like to see what kind of labels are there present.
How do we count for the unmatched? We just add.
Yeah, we can, when we build the table, we'll have to be careful and say that for the vertices that become unmatched in N, which were matched in M, we will have to say that some more votes get subtracted, right? Okay, so this is A1, this is A2, this is A1, A0, this is B1, B0. But having said this, suppose I give you a matching in which, suppose I give you a matching N, and you took the edges of the matching N which were not present in the matching M. You have labeled all the edges already with this plus minus. You just sum up the votes of the uncommon edges, right? The edges which are present in N but not present in N. You just sum them up. If the sum turns out to be negative already, right? If the sum of the votes, that is plus the number of plus ones that you had and the number of minus ones that you had, it turns out to be negative, does that say anything? Which matching is less popular? There are 2 matchings, M and N. So I have a matching. I have a matching M. I have a matching N. I take all edges of N not present in M, and sum up the votes. And this number turns out to be a negative number. What can I say? Sorry?
It's not preferred.
Which one is not? N is not preferred, right? So N is not beating M in terms of popularity, right? So it is a safe thing for us to have. Suppose this, I do the same thing, and the sum turns out to be a positive number. Yeah, so N is better is not immediate, but because maybe we have not summed up the votes of the unmatched vertices. So let's say we also take care of summing up the votes of the vertices that become unmatched, and then look at the sum, and that turns out to be positive, then what happens? Then N is better. So if you look at the sum of the edges and also do a careful counting of the votes of the vertices that become unmatched, and even after doing that, because these unmatched, the vertices that become unmatched are favoring M, so they are going to give negative numbers. So even after doing that, if you get a positive number, then you have a matching which is more popular. That is a bad thing to happen, because then our matching is not popular. So our goal is to show that bad thing does not happen, right? Okay, so in this slide, we would like to, so is the goal clear in terms of why we actually did all this labeling and all, right? Okay, so in this slide, we would like to label the edges which are with this lens, this picture, right? And we know that there can be unmatched vertices here, there can be these matched edges, there can also be an unmatched vertex here, right? So Let's now draw unmatched edges because only the unmatched edges are being labeled. So first let's ask the following. There can be an unmatched vertex in A1 and there can be an unmatched vertex in B0. Can I actually draw a direct edge between these vertices? An unmatched edge between these vertices. Okay, why cannot I draw it? Such an edge could be added. In fact, the Gale and Shapley algorithm itself gives you a maximal matching. You are doing Gale and Shapley and this higher priority. So you cannot leave two vertices unmatched like this because that edge could have been two vertices which are connected by an edge unmatched, because then you would have added that edge. If you want to think of it in the proposal sense, this vertex, if there was an edge, it must have proposed to its neighbor and therefore either this vertex is matched or this vertex gets matched. So therefore this edge between two unmatched vertices cannot be there. Clear? Similarly, can we have an edge from an unmatched vertex to somebody here directly? From an unmatched vertex to this vertex which is matched, of course. So maybe I'll just draw it to this. So okay, so I have first said that there cannot be an edge from an unmatched vertex in A1 to another unmatched vertex in B0. But let's ask, can an unmatched vertex in A1 have an edge directly to any vertex in B0?
No.
Okay, why?
Then we would have taken that in this round when it became a starred vertex.
So remember the way the vertices propose and the rule that was given, that if a starred vertex proposes to a vertex which is currently matched to a lower priority or unstarred vertex, then it must accept the proposal from it and get matched to it. So therefore such a vertex A0, such a vertex in A1 cannot have an edge to a matched vertex here also. So in fact unmatched vertices in A1 cannot have a direct edge to vertices in B0, right? So such an edge, I am not saying that these vertices cannot have, but a direct edge from an unmatched vertex is not possible. So there cannot be an edge from an unmatched vertex in A1 to another vertex in B0, that is not. Because it can neither be to a matched vertex nor be to an unmatched vertex, right? Okay, so now, but there can be edges like this. So this vertex is always matched, but yeah, so I should draw this as a black edge. And it can have edges to an unmatched vertex. Okay, so this is black and blue, but okay. So there are these edges, right? Okay, so let's ask first, when there is an edge which is complete, a blue edge which is an unmatched edge which is completely contained inside one of the partitions, that is A0 B0 or A1 B1, we would like to fix its label in terms of this plus plus or plus minus, right? So what is the sense that you have in terms of what can be the label of such an edge which is completely residing in either A0 B0 or A1 B1? Plus minus only or
minus minus.
okay. Anybody else? It cannot be a plus plus edge, right? Because they used, we have used the normal Gale and Shapley here, and we cannot have things like, we cannot have a plus plus edge here because that is a clear blocking pair. So these edges, and what edges are actually problematic? These plus plus edges seem to be problematic because if you have a plus plus edge, along that we lose both the votes. right? So maybe it is a good idea to actually label this and also draw the partition. So this is the matching produced by our algorithm. I hope it is clear that this edge is a plus plus edge and therefore it is also a blocking pair with respect to this matching. But what is the partition structure with respect to this, which is A1, which is A0? So which vertex gets a higher priority? In this example, so yes, the matching is A1, B1, A2, B2. Which vertex gets higher priority and is in the star state? Star. A1 gets a star and it gets matched to B1, which was earlier matched to A2. It kind of pulls it from A2 and then A2 goes and proposes to B2, but A2 doesn't get a star. Right? So, is that correct? Yeah. So then in terms of this partition, we have, this is the way. Right? So this set, the capital A1 set contains little a1, A0 contains A2 and so on. Correct? Okay. So while there are no other unmatched edges here, there is this one unmatched edge. But what we are talking about is these blue edges which are completely contained inside this partition, and all of us agree that these blue edges cannot become plus plus edges. They can be plus plus, they can be plus minus, they can be minus plus, or they can be minus minus.
You have some crossing from A0 to B1. But
A0 to B1, yeah.
But you haven't really analyzed this.
Sure, so this crossing in the sense A0 to
B1.
I'll do that. We are still analyzing only the edges which are completely contained here or completely contained here. We have only finished completely contained here. Right? And okay, even with this edge, we know that this is a plus. But what about this? This endpoint, it has to be a minus, because if it were a plus plus, again it is a blocking pair. So therefore, it has to be a plus minus, minus plus, or a minus minus. Right? What can we say about all the unmatched edges inside this partition? What kind of labels will they get? So recall that even here we have kind of run the Gale-Shapley algorithm amongst vertices which have received the star status. Right? So again all these edges, all these unmatched edges are there. They cannot be plus plus edges. There cannot be plus plus edges which are residing here completely inside, because a vertex here must have made a proposal to, if this was a higher preferred vertex for it, it must have made a proposal. This vertex was matched to another vertex with a higher priority. Amongst two star vertices, the actual preference is taken into consideration, and therefore if it got rejected, actually this vertex prefers its current partner and therefore it is going to give a minus. Right? So therefore there cannot be plus plus edges here, there cannot be plus plus edges which are completely contained inside the A0, B0. Right? So edges contained unmatched edges contained inside A0, B0 or A1, B1 can't be plus plus. Is it okay? Okay. But there are plus plus edges, right? Our example shows that there are plus plus edges, right? So we would like to also analyze. So of course our example also shows that the plus plus edge arise as this A0, B1 type of edge. So we should grant ourselves that in other instances also there can be edges from A0 to B1 which can be of the type plus plus. Need not be that all edges of that type are plus plus. But if there is a plus, there can be plus plus edges which go from A0 to B1. So what is the set that remains to be analyzed? Sorry? Cross, but this cross we have already given ourselves that maybe there are plus plus edges here. The one that remains is A1, B0. Right? So let's ask what can be the label of A1 B0 edge? If there is an edge from A1 to B0, what can be its label? Can it take the label, any of these labels, which are the 4 labels?
Must be minus, right? From A1 side.
Okay, so from A1 side it should be minus. Why?
Otherwise it should have taken it in the execution.
Sorry?
It prefers the one.
So once this vertex, so let's call this vertex as some A3. So let's say it got a star status, it starts proposing in the order of its preference. So if it has proposed to this vertex, it doesn't prefer this vertex, it goes in the order, and therefore it should be a negative one. If it would have proposed to this vertex is already matched to a lower preferred vertex, so there is no reason for it to reject it, and it should have gone higher. So from A3's side, it should always be a minus. What about from, let's say this, we call it as B4. What about from B4's side? It can be anything.
Because in normal case, it would have preferred the star. But the very reason the star got star is because it was not even matched.
Good. So remember that A3 before becoming a starred vertex must have proposed to B4 in the lower level or without getting a star, and A3 must have gotten rejected, which means that the currently matched partner of B4, which may be A4, must be more preferred by B4 over A3, not A3 star but over by A3, and therefore from this side also this edge must be this edge must be labeled minus. Is this argument clear to everybody? Okay. So then what we have established is, this is not only for this A3 B4 edge, any edge that goes from A1 to B0 is a minus edge. We know that A1 B1 does not contain a plus edge, A0 B0 does not contain a plus edge. If there is a plus edge, it can appear in the A0 B1. This thing, right? So there is no, so in fact all edges, all unmatched edges of the type which are A1 B0 are minus. And if there is a plus edge, it can appear only from A0 to B1. Right? This is all that we have established. Correct? So now we have all the right things to kind of complete the argument. So now let's take any matching n and look at the matching n and the comparison with respect to m with this lens, right? So always I am going to draw the black wiggly edges as our matching m, the blue edges as the matching n. So let us say that let me pick an arbitrary vertex which is differently matched in both the matchings, because if it's the match in the same way, there is no point of considering that it votes the same. So let us say that it is unmatched with respect to our matching m, so it doesn't have a black edge, which means that it must reside here because we have already identified that. So let's say that it takes it will have some unmatched edge, but it has a matched edge in with respect to the other matching, which is n. So I draw this edge. Now we also know that this edge should be in B1 because it cannot directly go to B0 because of one of the statements written there. Now can we leave this unmatched? No, because all the vertices in B1 are matched. So therefore we will take a black edge. Now we will keep doing this. So this possibly is unmatched like this. So this is matched to somebody else here, and we keep doing this. Where should I stop this exploration? Where should I stop this? Okay, so I am starting with a vertex. Let's call it A0. It is unmatched in our matching, so it does not have a black wiggly edge incident on it. But it is differently matched with respect to our matching and the matching n that I am interested in. N is an arbitrary matching, but I am just asking how does n look like. Suppose A0 is not matched in M and not matched in N, then we will not say that it's differently matched. So it doesn't vote for between the two matchings. So A0 is unmatched in M and it is also it is matched in M. It is unmatched in M and it is matched in N. Therefore, there is a blue edge. So in terms of this picture, it starts with A1. It goes to B1 because it directly cannot traverse here. So it goes to B1, but as soon as you go to a vertex in B1, you must have a black wiggly edge because all the vertices here are matched. So you must take this. Now can you stop here? Maybe this vertex doesn't get a matched edge, matched blue edge, but suppose it goes, then it goes, maybe it is still in B1 or it traverses and goes to B0. In this picture, I am just looking at it in this picture. Now the only two ways for this to stop is either maybe it stops like this or it just stops in the following way. Sorry, it should stop here. Is this okay? These are the only two ways for it to stop. Is there any other way? So it starts with an unmatched vertex in our matching M. Maybe this exploration stops at an unmatched vertex in our matching M, or it stops with a vertex which is unmatched in the other matching N. Right? In which case I cannot draw a blue edge incidentally. Is this clear? But in terms of this picture, we have to ask how does this picture fit into this set of vertices here. If it started with an unmatched vertex, we started here, we went here, maybe we went, this is only representative, so we went for a long time here. We could have come down because if this vertex has to be unmatched, where should it belong to? We cannot stop here. Yes.
We went from A0 to B1 using this blue.
Yes.
Why are we? Is it returning through a matched edge or?
This is a matched edge, right?
So we can return through some other blue.
There cannot be two blue edges incident on these are okay. So blue are matched edges in N, right? So we are now looking at another matching N, with respect to which we are looking at, because we need to compare M and M with any other matching N, and we want to show that M doesn't lose votes, right? That is our goal. And now, okay, so maybe the blue color is confusing, but whenever I draw blue color with these two lines, it means that it is a matched edge in some other matching, right? So, and why did I consider A0? Because A0 is differently matched in M and N, and since it is unmatched in the matching M, it must be matched in the matching N. So it has this blue with the line, this thing, it has a matched edge in N. Now it comes, and so therefore you cannot draw two blue lines on a vertex, neither you can draw two black lines. So you come like this. But where does this stop? If it stops here, it must end in B0, right? Because we don't have unmatched vertices here. So now how do I fit this path here? It goes here, it goes here, it goes here, and then possibly it has to do something here to come here, right? So I mean, yeah, so you can fit this entire path in this way here so that B0 finally lies here. We don't care about where these two vertices are. We know that this one vertex cannot be in B0. This vertex can be in B0 or in B1, doesn't matter. But what do we know about these edges? I mean, so when we go from this current matching, which is the black matching, and we shift to this blue matching, only if we shift along this part and retain all other edges of the black matching, what is the vote difference that we will get? So what is the label of this edge? We don't know, but we know that it is not a plus plus because it's completely contained inside here. What do we know about the label of this edge? It depends on whether we are traversing this or we are retained inside this. If this entire path, okay, so this entire path cannot be retained. So let's say that if we have this path, we must have gotten at least one edge which is a A1 B0 edge, which is a minus minus edge, right? So we have gotten at least one minus minus edge. Maybe we did this. Maybe our path was not this simple. It came here So now I will put the labeling with respect to this. So all of this was B1 till here. We traversed, this is A1. This is actually B, the partition where we go to B0. Maybe we did not stop here. We came here. And there is also availability to go up. So we went along a matched edge here, like this. We did some more work here.
But in total, there must be one more downwards cross edge.
So this edge could have been a bad or problematic edge for us, which is a plus plus edge. But then if we have to stop like this, we better take another favorable edge for us, which is a minus minus edge. Right? So if our path looks like this, that is, it starts with an unmatched vertex here, it ends with an unmatched vertex in it starts with an unmatched vertex here and ends with an unmatched vertex in M, then it must start in A0 and end in B0. It may traverse these partitions multiple times. Each time it goes, it comes down, it catches or it picks up one minus minus edge. And so as many times it goes up, it has already made up for that to go by going down. And note that even if it does it once, we recall that the endpoints of this path, are going to vote for which matching? The new matching N, because in that matching they get matched, but we have already compensated for the votes by picking up at least one extra minus minus edge than the number of plus plus edges. Right? So therefore, whatever work you do in terms of the above path, it is only plus minus or minus minus. Whatever work you do here, it's again plus minus or minus minus. If you cross these partitions, then once you cross it in this way, you have gotten a minus minus edge, and you must have picked up at least one minus minus edge more than the number of plus plus edges, which compensates for the two endpoints which are going to vote against the matching M. Right? So if you flip or if you change the matching M in along this way to get another matching N, you will never lose votes. Is that clear? Yeah. Now you can do this argument for such a path also, which is going to end here or which can end here, which ends either here. So I believe it should be clear that if the path is completely contained inside this partition A1, B1 or A0, B0, such a path cannot be contained because it has to start here. So if it is completely contained here, then it cannot gain votes because the edges are labeled as plus minus or minus minus. And similarly, what is one structure that we have not done which can arise? There can be other kinds of paths, because you can start with a matched vertex in M, which should look like this. That is, I started with a unmatched vertex in M and ended either at an unmatched vertex in M or a matched vertex. I can also start with a matched vertex in M and end at some other place, that is a matched vertex in M or an unmatched vertex in M. But there is another structure which is not a path. What is that? A cycle, because all the vertices are matched in both M and N, but they are differently matched. So a cycle with respect to this looks like this. These things also have a very nice name, which are called as alternating cycles. So this is an NH. I'll draw a 4 cycle or a 6 cycle maybe. But then how does this cycle look like? Again, how do I fit this cycle? If I fit this cycle entirely in this A1B1 part, there is no problem, because there are only plus minus 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 edges. If I fit it completely here, there is no problem. If I fit it across, then at some point I must have taken an edge which goes down from B1 to A0, which is of this type, and I can also take an edge which is of this type, which is going from A1 to B0, but then as many plus plus edges that I take, exactly so many minus minus edges that I take. Therefore, the votes again compensate, and the votes of everybody are counted here in a cycle, because all the vertices are matched in N. Therefore, if I take some T number of minus minus edges, if I take T number of plus plus edges, I must have also taken T number of minus minus edges, and therefore the plus plus votes actually compensate. A naught to B1 can be a but that is the only plus plus edge, right?
It can be plus 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 minus or it can be anything.
It can be anything. So only if I have plus plus edges I am in trouble, right?
Yeah.
Because if I have minus minus edges or plus minus edges, they are not troublesome for me, right? So using this argument, you can show that even if the cycle fits across these things, then as many plus plus edges you have collected, you have collected as so many minus minus edges, showing that along any of these structures you cannot get a matching which is, or you cannot get a structure which beats M in terms of popularity, and these are the only structures using which you can change from M to N, and along any of these structures you cannot gain vote, and therefore M must be popular.
And it deleted these structures in the case of a vertex which is matched differently and but is not unmatched.
So yeah, so I mean maybe I did not do everything completely, but you have to look at a vertex which is matched differently in M and N.
Yeah, and that is not unmatched in M.
Yeah.
What about those cases?
What is?
If the whole graph is matched in M as well as N.
Then you will always have structures which are cycles, right? So if you have the entire set of vertices which are matched in M and in N, that is the sizes of the matching are exactly the same, right? M and N.
Okay, I have
Okay.
a question. So we start with a vertex that is matched in M and matched in N, but differently.
Correct. So that is like this, right? So it is matched in M, which is this edge, matched in N, which is differently.
So which is the order through which we?
Okay, so let me just do this. So this is a vertex A naught which is matched in M. It must have a blue edge, right? Because it is also matched in M. Do this. Now what will happen with respect to this? This vertex can either be unmatched in N or unmatched in M or matched in M. If it is unmatched, you will stop here.
Yes.
So then if you stop here, let's
Yeah.
stop here.
Okay.
Ask the vertex the same question. Are you matched in M or N? And what should you do? Either you draw this edge or stop here. So you will either get paths or cycles. Does it make sense or is?
Yeah, it does make sense.
Okay. Sure. So just to conclude, so yeah, there are some gaps to be filled up because I did not do all the cases completely, but I hope you get the essence of it. That is, you get structures which are either paths or cycles. The paths can be of different types. They start with an unmatched vertex in M and they can end in an unmatched vertex in M, or they can end the matched vertex. Those two cases we completely did, and then there are cycles which we completely did. We did not do one case which you can work it out yourself, but along these structures you cannot gain votes, and these are the only structures which allow you to change M from M to N, and therefore you cannot get any matching N does not get more votes, right? We still did not show that M is a maximum cardinality amongst all the popular matchings. M is a maximum cardinality popular matching, but we will not do that here.
There will be several structures first.
Actually, there are not several. There are only, okay. So I'll just maybe list it out. So you start. So A naught. So it is unmatched.
No, I meant something different.
Oh, sorry. Okay.
Several, as in the number of these.
Yes. There can be several of these structures. There can be multiple of these structures when you look at M and N, which are differently matched. But along any of them you cannot gain votes. Therefore, N cannot get.
But and in several of those structures of the same kind or anything of these kinds, edges won't repeat.
Edges won't repeat, right? Because once you use an edge, these are edge disjoint. These are actually vertex disjoint structures. Once a vertex is matched in along a black edge, it cannot appear in any other structure, right? And therefore the votes are distinctly counted. Thanks. Yeah, it's a good point. Yeah, so these things are called as symmetric differences. But I'll just say this. So this is A naught is unmatched in M, and then you can end the path in some BK, which is either unmatched in M or matched in M. So these are two cases. which we considered already, and then A0, I mean I'll say A1, it is matched in M, and then again BK, so these are 4 cases, and then there is a cycle. So these are only the 5 cases that need to be considered. We considered one of these 2 and the cycle, and we did not consider this, right? And yes, of course there can be many such structures, but along each of these structures you do not gain votes, and therefore it must be the case that M cannot be beaten by any other matching N. Right? Okay. So yeah, I think I'll just stop here. Just give me 2 minutes to wind up in terms of what we did. Yes, but you had a question.
I just gave me an idea that maybe we can make something like a modified IISc algorithm by looking at this proof and trying to construct a maximum n. I mean, we know in this proof we actually know that there is no n which is better than m. Maybe we try to construct such an n. We don't actually have an m initially. Let's assume we don't have an n. We try to construct an n which is supposed to be the best. We come across these kinds of structures, and instead of disallowing them, we allow them, and in that way grow it so that we get.
Actually, we are allowing them and we grow them. That is what the modified Galen-Shapley does. Yeah, thanks. Yeah, so I just want to state, so in the last, yesterday's class, 2 classes, and today's 2 classes, we have seen the stable matching problem, the very celebrated Galen-Shapley algorithm which computes the stable matching. We saw some nice properties of the stable matching produced by the Galen-Shapley algorithm, as well as properties of the stable matching. We have just, as Prajakta said, we have just scratched the surface. In today's class, we have looked at a different notion which is called as popularity. We have given a modified Galen-Shapley algorithm which gives popular matching, and we have shown that it outputs a popular matching, but it need not, we have not shown that it admits amongst all the popular matching a maximum sized matching. That is something that you can read up in the paper that Prajakta did. Yeah, so I thank all of you for your attention and participation, and once again the organizers for inviting me. I overshot the time too much.
No, not at all. But
Yeah.
we have time.
But yeah, I did not.